Hello everybody. So a flipped teaching presentation for method of sections. We'll be doing this in a simple example during the lecture, so it would be a good idea to have a look at this one before the lecture. Okay, so concept with method of sections is we imagine that we've got a framework, and with method of joints we imagine that we cut around a joint. So method of sections is a bit like method of joints. The same thing we do is we cut around the joint, and by cutting around the joint in method of joints we expose the internal forces. So I imagine I've cut around my joint, and then I'm going to label up these internal forces. I'm going to label that one as AB, and label up this force here as AE. Okay, so it's really taking that idea of the method of joints one stage further, and not cutting around a joint, but cutting actually through the framework. Now the reason why I can cut through the framework and not just cut around one joint is because if I cut through the framework and I cut so that I cut through 3 members, how many unknowns do I have? Well, let's go back to what we should know about method of joints. So method of joints, I know I should start at a joint where there's only 2 members. So I could start at A, or I could start at D. There's nowhere else on this particular framework where I could start. So those 2 points there. Why do you start where there's only 2 members? Because when you cut through the joints, you're creating 2 unknowns that you're looking for. So we could cut around A, or we could cut around D. Okay. And the reason why we're looking to just cut around a joint with only 2 unknowns because we're going to only have 2 equations that we can tackle those unknowns with, which is summing up the forces in the x direction, which includes the exposed internal forces, and summing up the forces in the y direction. So you are then going to sum up those forces, which are the internal ones and also the external ones that are being applied at that joint. So it's only the ones that are being applied at that joint. So we can take those forces and put them into these pair of equations here. Now what I can do with method of sections is I'm going to have 3 unknowns. Going to cut through the method of section at 3 unknowns, and that's normally good enough for most frameworks. We can apply that. So what's going to be my third equation? Well, you've probably guessed it's going to be take moments somewhere, and it's going to be take moments anywhere you like. A good place is to choose some joint somewhere on the framework that you're going to have. So what you can imagine we're doing is we're doing a big method of joints, but we're cutting all the way around like that. So I'm cutting through these members. That will expose these 3 forces, which I can then sum up in the x direction, the y direction, and then thirdly I can sum up moments at any location I like, particularly for whatever part of the framework I keep. In this example here, we've cut through the framework through the middle, and I decided to keep the left hand side. Normally it's nicer to keep the left hand side because the arrows then are kind of pointing left to right, and it's kind of nicer to deal with arrows pointing left to right. There is some cases when it might be more prudent to actually keep the right hand side of the framework and throw the left hand side of the framework away. Okay, so anyway, in this case we've decided to throw the right hand side of the framework away, and we need to keep the external forces that are being applied on that right hand side. So there was this 81 and this 3.33 force here, so we need to keep them, and then we need to relabel our members that we've cut through as forces. So that's going to be a force, that's a force, and that's a force. So cut the framework where you want to calculate your internal forces. Cut the members and replace the external forces from the throwaway piece of cut framework. So we've thrown away the right piece, and those members that we've exposed, we're going to call them internal forces. Here it's going to be BC, EC, and FEF. Only consider now the forces for the analysis. So we are only looking to find out what these values are. Okay, these values we're going to use in our calculations, but we already know what they are, so we're just going to leave those forces as part of knowns that are going to come into our calculation. So let's go back. We've cut through the framework, we've thrown the right hand side away, we've relabeled the cut through members as if they are forces, and they're forces going in the members direction. So that's a BC one, that's an EC, that's an EC1, and that's an EF1. Okay. So this is really good method if you want to look for a specific member somewhere in your framework. So it means you can probably, provided you can not have to cut through any more than 3 members, you can cut through that member, and then that'll be enough for you then to find it. If we were far away from our, typically, not always, but typically it's our reaction points. If we're far away from our reaction points for the member that we're looking for, that would mean we'd have to go through, jump from lots of joints one to the other in order to get to the framework that we're looking for. So that's why it has that advantage over method of joints. The external forces for the on the piece of the framework that you are keeping, you mustn't throw them away. You're going to apply the equilibrium of moments as well as the equilibrium of forces. So we've got 3 equations and 3 unknowns. Determine the unknown external forces using a new free-body diagram of the structure that you've got left. Cut the framework into sections at the point where you are trying to determine the member's internal force. Assume, like with method of joints, that each member is in tension, i.e. that there's a force pointing away from the joint. Resolve any angles in the XY components, or maybe you want to skip this step but do some geometry so that you know how to deal with them when you go to this step here, which is then to apply the 3 equilibrium equations and then solve your unknowns. Okay. So here's my example to demonstrate it. I've got a big box bridge framework here, and what I'm going to be interested in is this framework in the middle here, this one here. So assuming that it's going to be resting either side of the river at these pivot points there and there. We're miles away from any joint, so we could start here, we could start here. So we could start method of joints at this point, or we could start method of joints at this point, because either A or N would be cutting around a joint with only two members. But you can see I'm going to have to do a lot of calculations to finally get to be able to either get to joint D or to joint E. For the problem, I'll set it up so that I have a nice simple 12 newtons force applied in the middle. I don't want to bother with complicated reaction calculations. So that means that I know what the reactions are going to be either side. So it's bang in the middle. That's going to give me 6 newtons going up as a reaction here, and 6 newtons going up here as a reaction. We've set this to be a hinge, so we've got 0 newtons being applied at the hinge. And it's this member that we're going to be interested in. Okay. So if we were doing method of joints, what could we do? Well, we might typically start at this joint A, and then from joint A you could then move on to joint B. Well, it's not joint B, is it? But so you could move out onto that upper joint, then onto B, then the upper one, then on C, then the upper one, and then finally we get to cut around joint D, which would mean I could then find out what DE is. That's a lot of work. That's not going to make me a happy baby. So what I want to do is imagine that we're going to cut around this whole framework, one big method of joints as it were. But it's, of course, it's not called method of joints. Now it's called method of sections. So we're cutting through these members here, and we're going to expose their forces. Now I'm going to throw away the right hand side, and I will then just look at the left hand side of the framework. So I've thrown away the left hand side, the right hand side of the framework, and I've relabeled up these cut through members as if they're forces. So we've got this internal force KL, we've got this internal force EK, and we've got this internal force DE. Don't worry too much about the initials. If you don't believe me, well, we could go back up if you don't believe me. That's the slightly odd way that I've labelled it up. So I've gone A, B, C, D, E, F, G, then H, I, J, K, L, M, N. Okay, so it's the KL force, the KE force, and the DE force that we're interested in. Okay, so that's where we are. So cutting through there leaves us with this external load that's been applied, this 12 Newton load, and it also leaves us with this reaction force, 6 newtons there. So let's go about solving what these three unknowns are going to be. So what I could do, I could typically see that EK is pointing downwards, so that suggests to me I want to resolve the force. That's the only one slightly pointing downwards, rather, so it's pointing downwards and pointing left to right, whereas KL is pointing left to right, DE is pointing left to right. So let's solve it by resolving the forces and resolving forces going in the y direction. So we've got 6 going upwards, we've got 12 coming downwards, and then we've got the EK, which needs to swing through 45 degrees here. So that's going to be EK swing through the 45 means we got, and then it'd be pointing downwards. So that gives us minus EK cos 45. So that's all my forces summed up. Now I can set that to be 0, so equals 0. Okay, so 6 minus 12 equals minus 6. And because we've got a minus here, when we take it over to the right hand side, we end up with minus 6 again on the right hand side. So have a pause if that maths seems weird. Double check that you're okay with that. We can use our calculator. Don't be a hero. We can put that into our calculator and find the answer. And then we can press on our calculator SD, the SD button, because most calculators will be, if you're using Casio calculators, they'll be set up to give you the irrational result. Press the SD button and then you're going to get the result as if it's in decimal places. So that gives me the answer for what EK is. Next, I could resolve forces in the x direction. Okay, so all these forces are vaguely pointing in the x direction. The EK needs to have to swing through 45 degrees again. So it needs to swing through, and then it'd be pointing bang on in the x direction. So we've got DE pointing in the x direction. So got that one. Then I've got EK. Provided I swing it through 45 degrees, that will be pointing in the x direction. And then we've got the KL pointing in the x direction. So we've got the DE, KL both pointing in the x direction. And then we've got the EK pointing in the x direction, but it has to swing through 45 degrees. Okay. Let's rearrange this so that we have the unknowns on the left and the knowns on the right. Well, there's actually only one thing we know, and that's from the previous equation, which was that EK was what was it? Forgotten. EK was this minus 6 root 2, or this number here. Okay, so put minus 6 root 2 times it by cos 45 when we end up with 6, because we've got basically 6 root 2 divided by root 2, and it's a minus value, so we've got a minus times a minus. So minus times a minus gives us a plus. 6 root 2 divided by root 2 leaves us with 6. So that's my answer for the right hand side. Now, what can we do? So we're going to have to do another equation, because we've got two unknowns, so we need to find another equation, and this is where your taking moments comes in. So we're going to take moments. Where's a good place to take moments? Well, it's not labelled up here, but that's the K joint up there. So you can see that K joint is the natural place to take a moment, because to set your pivot, because you've got two unknowns, although one of them has been found. You've got two unknowns coming out at that joint. So that wherever you have your two unknowns, that's a good place to take moments. So we'll take moments at that point. I think it's 1 meter, isn't it? These are horizontal and vertical distances. So it's 1 meter from here to here. This force is going straight through the pivot, so it doesn't create a moment. There's no turning effect, although it's kind of pushing against the pivot, or pulling away, sorry, against the pivot. So here we do have a turning effect. We've got DE, and it's a distance of 1 meter. So if I take moments in a clockwise fashion, so we're going clockwise, that means that my clock is turning a different direction to where the force wants to turn, so we're going to have a minus value. So minus DE times 1. Okay, what other turning moments can I see? Well, there's the one out here, so that's the 6 meter. 6 newtons, sorry. And what I'm going to do is I'm going to bring that force and bam it here so that it's in line with the pivot, and then I'm going to measure its distance. So it has a distance of 1, 2, 3, and it has a force of 6. It's now actually, imagine the clock turning, it's now pointing in the same direction as my clock, so therefore it's going to be positive, so it's a positive moment. Plus 6 times 3. Oh, that's easy enough to rearrange. We've got minus dE equals well, minus dE plus 18 equals 0. Rearrange that and we end up with dE equals 16 newtons. And because it's a positive value, we can say that we know dE is going to be in tension, which is what we were being asked to find in the original question. Okay, so that's it. Did you notice that I did a stupid moment there? Can you spot it? I did it deliberately, to be honest with you. My original question asked to find what dE was. So although I started off by taking this problem and resolving the forces in the y direction, I didn't need to. I didn't need to find out what EK is. And I certainly didn't need to resolve forces in the x direction. That just left me with this equation here. That's a very nice equation, but not much I can do with it. However, if I had done this in the first stage, I could have found out what dE is from the start. So I've done an awful lot of maths there which was unnecessary, but I did it on purpose to take you through the process of summing up the forces in the x and the y direction, and then showing you that you don't necessarily have to solve it in the x and y direction for a particular problem in an exam scenario. Okay, who wants to go to Clifton Suspension Bridge? We could all go and have a drink, have some fun. Okay, bye-bye. That's your flipped teaching. Look, it's a star.